Hello, everyone, and welcome to the Dean's Lecture Series online. My name is Peter Log. I'm the Dean of the Faculty of Science here at the University of Victoria, and it is a real pleasure to welcome you all to today's lecture by Dr. Natasha Morrison, called The Mathematics Behind Map Coloring. Now, before I start, I would like to do what we usually do at the University of Victoria. That is, I would like to acknowledge and respect the Lekwungen peoples on whose traditional territory the University of Victoria stands, as well as the Songhees, Esquimalt, and Wisanish peoples whose historical relationship with the land continue to this day. Now, when I first started as a dean, almost 2 years ago, I was very pleased that I have my own lecture series, the Dean's Lecture Series. But then it was quickly pointed out that it's not the Dean apostrophe S lecture series, which I thought, my lecture series, but it's the Dean's apostrophe lecture series. So that is, it belongs to all deans. So that makes a bit of a difference, right? But at the same time, I think we can all agree that the talks from the Faculty of Science really are the best talks. And it is a real pleasure to have Natasha Morrison here today. The talk today is about coloring maps. So if you had asked me a little while ago, I would have said, well, this is either a trivial problem or it's a really hard one. And when I looked into it, I actually learned it was an unsolved problem. So I'm really curious to hear that apparently it has been solved, and would like to hear what Natasha has to say about it. A few words about Natasha Morrison. She joined the Department of Mathematics and Statistics only in 2020, so she is quite a recent hire. She had obtained her PhD from the University of Oxford and then spent time as a postdoctoral fellow at the University of Cambridge. That also, I thought, was not possible. Can you really go from Oxford to Cambridge? Well, apparently you can. She then spent some time at the Instituto Nacional de Matemática Pura et Aplicada in Rio de Janeiro in Brazil. When she moved here to Victoria, she has now an opportunity to work as an independent researcher on a wide range of research interests, mainly in the area of extremal and probabilistic combinatorics. So broadly speaking, these fields concern understanding of the structure and properties of large-scale networks and how processes in networks, such as the spread of disease, behave in different environments and under different settings. So I'm really looking forward to today's talk, and again, welcome all. Thank you.
Hello, everyone. Thank you very much, Peter, for the very kind introduction. So today we're going to talk about a problem that I think is very interesting in the area of combinatorics and graph theory. You might find it helpful if you get a pen and paper, so maybe try various things at points of the talk. Pause the video now and get a pen and paper so that you can try some little examples when we get to that point in the talk. Today I'm going to talk about a problem that's very related to my area of research, which is combinatorics or graph theory. So what I'll do is I'll start by introducing the problem. We'll then talk a little bit about how a mathematician might approach this sort of problem. We'll go through the history of the problem, and we'll talk about my general area of research as well and how this all connects. And we'll conclude by, I guess, solving the problem. So I want you to imagine a map. So I've picked a map of the States of America just because it's a fairly complicated map, but not too complicated. I want you to think about the question, how many different colours do you need if you want to colour the regions of this map in a way so that bordering regions always get different colours? So suppose you wanted to do this using the fewest number of colours possible. How many would you need? So the best way to approach something like that is just to start trying to colour it in. So, okay, so let's colour the sea, let's colour the sea blue. In fact, if we want to use a small number of colours, we actually want to colour some other regions blue as well. So, okay, I've just picked some arbitrary regions I'm going to colour blue. I'm now going to try and colour the rest of it. And again, remember that bordering regions are not allowed to get different colours. So now all of these regions which have a border that shares the border with the blue region, we can't colour that blue. So we can colour some things red. We're still not done. So, let's put some yellow in. And now we can see that actually it is possible to colour this map in 5 colours so that no 2 regions that share a border have the same colour. Okay, so that's great, but we did colour this kind of arbitrarily. So 5 is enough. Is this best possible? So perhaps if you get your map and you colour, so it took me a while and I tried a number of different ways of colouring this, but in fact it is possible to do this map in 4 colours. Okay, so as a mathematician, at this point you might say, okay, I can do it in 4. Can I do it in 3? If I can't do it in 3, what is the reason for this? Why can't I do it using 3? So let's zoom in on a little bit of the map here. Okay, so this is just, I guess, the top left-hand region of the map. And if we look at the kind of regions I've coloured pink, let's see, how do we colour these regions? So the middle one has to get a colour. Might as well colour that blue. Now, if we try to colour the rest of these using in total only 3 colours, then okay, so anything that touches this blue one can't get blue. So we might as well, let's colour one red. Now, this one touches both the red and the blue, so it can't be red or blue, it has to be yellow. If we're only using 3 colours, we're only allowed to use red, blue and yellow. So therefore, we're forced to colour this one red, we're forced to colour this one yellow, but now we're stuck, right? It's absolutely impossible to colour this small section of our map using only 3 colours. So we're kind of happy as a mathematician, right? We've shown that we can colour the map using 4 colours. We've shown that we can't colour it using 3 colours. So for this particular map, we've determined precisely the smallest number of colours we need to colour the map in such a way that bordering regions do not get the same colour. So we picked one particular map, right? The map of the states of the US. What about any map? And when I say map, let's think about this in a more general sense of the word. So it doesn't necessarily have to be a map of regions or countries. You can imagine a map to be, right, take any piece of paper, draw any set of regions, scribble on the paper, try and draw, make up your own countries, right? Anything that you can draw in this way, we consider to be a map. And so the more general question you might want to ask is, so for any kind of map drawn in this way, what is the number of colours you need to colour it so that bordering regions get different colours? So is it possible to draw a map that requires an arbitrarily large number of colours? Can I draw a map that needs 100 colours? Can I draw a map that needs 300 colours? So all we've done so far, we've shown that this one map of the USA can be done using 4 colours. We haven't said anything about any other map. So in particular, we haven't found any map that even needs 5 colours. So if you were a mathematician kind of trying to think about this problem, right, what we've done is we've taken one example. We said, okay, we really understand this example. We understand that it needs 4 colours, can't be done in 3 colours. At this point, you want to try and understand something a lot more general. So now you say, okay, what about a wider class of objects of this type? What can we say? And at this point, you might try other examples. So I Googled, colouring pages for adults, and I found this nice frog. And I tried to colour this frog using 4 colours. And it was kind of fun. I did colour it using 4 colours in such a way that bordering regions do not get the same colour. And I would encourage you to go find a colouring page and go and try and colour it in such a way. Right? Can you do it using 4 colours in a way that bordering regions get different colours? You might have to print it multiple times because you'll probably do it one way, you'll get stuck, and you'll have to start again. But this is the way that we can explore the problem. We can try different examples. We can see, what things are going on. Why is it the case, as you will see if you try to do this, why is it the case that we can actually always do this in only 4 colours? So let's think about this more abstractly. What would be one reason to need 5 colours? Okay, well, one reason could be if we can find 5 regions such that every pair of these regions shares a border, then these 5 regions would all have to get different colours. So okay, let's take a piece of paper, try and draw 5 regions with this property. So this was my attempt. So I've drawn one region, right? I've drawn another region. It shares a border with my first. Okay, so the third needs to share a border with 1 and 2. Okay, so now I'm going to draw my 4th region. Now at this point you've got some choices. So I drew my 4th region, right? So I've drawn it in a way that I'm sharing a border with the first region. I'm also sharing a border with the second region. But actually, right, in doing so, I've completely surrounded my 3rd region. Now, there are different ways you could draw this 4th region. But actually, every way, so you could start next to region 3, you could go all the way around 1 and hit 2 on the other side. But you'd still end up completely surrounding region 1. And similarly, if you started at region 3, and again you went round 2 to get to 1, you would completely surround region 2. So actually it's not possible with only 5 regions to come up with a map that needs 5 colours. This doesn't tell you in general it's impossible, because perhaps you've got some set of regions that force some colouring pattern over here, there's some set of regions that force some pattern over here, and together, all together, you end up forcing things that might need 5 or 6 colours, right? So all we've observed is that we can't come up with a small example that causes a problem for us. So the general question we're trying to think about today, is it enough to have just 4 colours? So hopefully you've gone away, you've paused the video and you've tried to colour things in, and hopefully you've realised that it seems like it is enough. The difficult thing is really why? Why is it just enough to have 4 colours? So as a mathematician, it's not enough to just observe that something seems to happen for a large number of cases. Right? What we're looking for generally in maths is a proof or a reason why this thing should be true, an argument which explains not just, oh look, we can see that in every case we draw, this is true, something which says this is always true. So let's talk a little bit about the history of this problem. So this phenomenon was first observed in 1852 by Francis Guthrie, who was colouring in a map of the counties of England and realised that it could be done using just 4 colours. So he asked the question, can every map be coloured with just 4 colours? So in general, I'm going to keep saying, right, can a map be coloured? Can this be coloured? Every single time I say that, I do mean with the condition that bordering regions get different colours. I'm not going to say that every single time. So when I talk about can something be coloured, this is what I mean. So this problem was actually recorded in a letter between De Morgan and Hamilton in 1852. Now, if you're a mathematician, these are names that you might recognise. These are kind of names of fairly big mathematicians. And so this is, I guess, a very long time ago. They were writing letters about this problem. And it actually, the problem appeared in the Athenaeum, which is a fairly prominent magazine in the United Kingdom in 1854. And so note the date change now. So in 1978, Cayley, who again is in the world of graph theory and combinatorics, a big name, asked about this problem at a meeting of the London Mathematical Society. And this is in 1978. So this phenomenon was first observed in 1852. In 1978, which is over 100 years later, nobody had found a map which required 5 colours. Obviously, everybody in the world was spending all their time trying to draw maps which required a lot of colours. But you've got a lot of very clever mathematicians thinking about this problem. And no one has managed to find anything that requires more than 4 colours. So when you're a mathematician, you're thinking about a problem. You want to say, okay, either 4 colours are enough or they're not. If they're not, then all you just need one example which requires 4 colours. That's called a counterexample. It would be a counterexample to the claim that every map only needs 4 colours. But suppose you can't find a counterexample. Well, at this point, you need to come up with a proof or an argument why, for any map that anyone could ever draw, infinitely large map, any sort of map, right, 4 colours suffice. So what is a mathematical proof? So I've said, right, what you want as a mathematician is to come up with a proof of this statement. So let's just take a step back and say, what really is this? What am I asking for? So in mathematics, we study many, many abstract objects, and we develop theories about the structure and properties of various things. We have things called mathematical statements about these objects. So the cool thing about maths is that everything is either true or false, right? There's no ambiguity anywhere. So for example, if I say to you, 5 plus 3 is equal to 10. That is clearly false. So if I said that 7 times 3 is 21, well, that's true. So what is a proof? Well, a proof is a logical argument why some statement is true. And this is an argument beyond any doubt. So at no point can you say, oh, we just looked at 5 cases and it was always true, so therefore it must be true. No, you have to argue from first principles, where each step is a clear logical deduction that can be verified by any mathematician who wants to read it, that will explain precisely why this is true. So yeah, as I said, right, you build a proof from a series of claims. So you start somewhere, and each step you logically deduce from previous claims. And the really cool thing about maths and proofs in general is it's very different from other fields where kind of facts are obtained by experiment and observation. So I guess in many of the sciences, right, the way that people determine what they believe about things is just by doing many experiments. And if, I don't know, for example, they want to determine whether a certain drug works to solve a certain condition, they will do a medical trial. They will observe that in 90% of the cases, this drug seems to help. So then they will say, okay, this drug helps cure this disease. We're going to believe this and let's go from there. I'm obviously oversimplifying other fields here. But in mathematics, right, everything that we study, we prove, and then we can use it as a fact. We don't observe and we don't guess based on a couple of examples, because a lot of the time you can take small examples for a property, and actually when you go just a bit bigger, you realize why whatever you thought was true or was not true is not. So we've got these maps. Now, I guess if you've sat down and you've tried to draw some of these maps, or you've played around a bit with the problem, but you might think, well, these are drawing regions. It's kind of hard to get a grip on this problem. You can take some map with certain regions and you can change the border of some region a tiny bit. It's the same map, right? The problems are kind of equivalent. So what we can do is we can actually find a mathematical structure that encodes the key information about this map, and then we can turn this problem from a problem of colouring the regions on a map to a problem of colouring the nodes on a particular mathematical network, which is called a graph. So probably the most common usage of this word graph is something that you see at school, where you have an x-axis and a y-axis. When I talk about graph, we're going to talk about a different mathematical object, which somewhat unhelpfully has exactly the same name. And hopefully it will be clear to you what I mean when I say graph after the next few slides. So how do we turn a map into a graph? So given your favourite map, for example, a map of Canada, we can add a node for each region. And what we're going to do is we're going to join the nodes that correspond to adjacent regions. So actually, colouring the regions of the map corresponds to colouring the nodes of this network in a way that nodes that are joined together get different colours. This is a mathematical network which is called a graph, and so graph theory is one of the main areas of combinatorics, which is my field of research. So let me just briefly take a step aside to tell you a little bit about graph theory. So networks are everywhere in the world. If you look around you, you'll see that many things that you encounter in your everyday lives can be expressed as networks or problems on networks. So for example, Facebook, right? It's a social network, but you can imagine that each person, each user is a node, and you connect to users if they are Facebook friends. Any kind of transport network. So for example, the London Underground, right? You can have a node for each station, and you connect to stations if you can get between them on a tube train or something. or in general, right, train stations, airports, anything where you've got kind of hubs and there's a reason for connection, you can express as a network. So what is graph theory? Well, graph theory is the overall study of the structure and properties of networks. This is what I spend a lot of my time thinking about. So here are some of the questions that graph theorists think about. So can we predict the way that disease will spread through a social network? How do we place a network of water pipes in such a way that we can reach all the towns but use the fewest meters of piping? So this is some kind of optimization problem on a network. How can we best design a road network in a way that we can minimize the time that drivers have to wait in traffic? So many real-world problems can be expressed theoretically as a kind of graph theory problem. So one possible thing that you can think about is there an efficient system to help people find kidney donors? This can be expressed as a problem in directed networks. And the question that we're thinking about today, what is the fewest number of colours you need to paint a map so that adjacent regions get different colours? Right, so what we've done is we've got our map question, we've turned it into a graph problem. So how do we visualise a graph? Let's just take one step back into a slightly more abstract setting. So formally, what is a graph? So a graph it's a pair, VE, where we'd say both V and E are set. So V is a collection of vertices, which are the nodes of the network, and E is a collection of edges, which are the connections of the network. So, right, the vertices are the things being connected. So in my two pictures, the little coloured blobs, they're the vertices, they're the nodes. The edges are the connections in the network. So each edge joins two vertices. Now, the important thing, it's the connections, not exactly how the graph is drawn in a picture, right? So, in fact, the two networks that I've drawn on the left-hand side here, they are the exact same graph. Every coloured node is joined to every other colour. They're the same graph, they're just drawn in different ways. And somehow this encapsulates part of the annoyance of the map problem, right? I've said if you have these two regions and you slightly wiggle the border between the two regions, essentially it's the same map, but you don't want to really consider this as a different case. If it's now a graph and what you care about is the nodes and whether or not they're connected, then this graph with the wiggly region, or this map with the wiggly region and the straight region, gives the same graph. So somehow thinking about this in terms of graphs is a much more sensible thing to do. So a technical word here, when we get a graph from a map, it's actually a special type of graph called a planar graph. What is this? Well, a planar graph is just a graph that you can draw on a piece of paper in a way that these edges, these connections, only intersect at nodes. So it's not the case that we're going to have, crisscrossy edges everywhere. So if you can think about this for a second, right? Take your favourite map, put a node in each region. You'll see that actually any graph from a map, you're going to be able to draw the connections in a way that they don't ever cross. So this is a really important property because this actually rules out a large number of graphs if you're not allowed to make your edges cross. One thing that's worth bearing in mind, right? It is possible to get a graph from a map and draw the edges in such a way that is called nonplanar, that is, in a way that the edges cross. But the important thing is that you can always draw it in a way where the edges don't cross. So whether or not they might cross in some other drawing, that doesn't matter. We're just going to restrict our attention to graphs where the edges don't cross. So what we've turned the question into is a question which says, can the vertices of a planar graph be coloured in 4 colours in such a way that nodes that are connected get different colours? So we took our map problem, we've turned it into a graph problem now. It's exactly the same problem. But now we're in graph theory, right? And we've spent time thinking about graph theory, well, not we, mathematicians have spent time thinking about graph theory. There are a whole load of tools and techniques that can be used to approach this sort of problem. So, as I said, what we want we want a proof. This is a problem from 1852. So not too long afterwards, two, again, fairly famous mathematicians both believed that they actually had come up with a proof. But if they had at that point, perhaps it wouldn't be so interesting that I'm telling you about it today. So unfortunately, they were both wrong. They thought they'd come up with proofs. They hadn't. So they were actually disproved by two other fairly well-known mathematicians, I guess within 10 years or so of when they thought that they'd come up with their proof. So okay, they thought 4 colours were enough. Fine, they weren't. I suppose a small consolation is that Hewitt did prove that actually 5 colours are always enough. So for any planar graph you ever want to draw, for any map, you can always colour it using 5 colours. So that's great and that's pretty cool. It's not 4 colours though. What we care about is 4 colours. So people continued to work on this problem throughout, I guess, the 1900s. And at some point in the 1960s and 1970s, computer-aided methods were introduced to help think about this problem. Now, why might this help you? Well, think about it. I guess, right, when you're trying to solve this sort of problem, you do inevitably run into quite a lot of case analysis. And that's something that a computer can do way faster than a human can do. So actually, in 1976, a computer-aided proof of this fact was discovered. They showed that for any map, for any planar graph, 4 colours are always enough. So what I want to do now is just talk a little bit about very broadly how a computer-aided proof might work, and also why, even though we have a computer-aided proof, we're not entirely happy yet. How, on a very, very kind of high level, how does this computer-aided proof work? Well, firstly, there are infinitely many graphs that you can possibly draw that are planar graphs. So there's no way you can possibly just ask a computer to check every possible graph, because it would never ever be able to do that. So the way that a proof works, or a computer-aided proof works, is somebody does some clever maths which will reduce the problem of checking all these graphs in the world to checking a much smaller number which a computer can do. So for example, let's talk about some very basic reductions that you can perform on these sorts of graphs. So I've got a graph on the left here. So let's have a look at it. Well, we've got a node here that's joined to only one other thing in this graph. Okay, so suppose you delete that node now. Any possible way you have of colouring what's left will extend to a colouring of the whole thing because it's only joined to one other node, right? And you've got 4 colours. So that it might be joined to a blue node, you can still colour it red, right? It's only got one restriction. So in fact, a very basic reduction you can do is you can delete any node that is only joined to exactly one other node, because once you colour what's left, all of these things can easily also be coloured. This idea actually extends to things joined to 2 or 3 other nodes, right? So I've got this sort of set of edges here in a particular node. If you were to delete that node, colour everything that's left, now have a look at this node, put it back in, well, no matter how you've coloured what was left, you'd always be able to colour it because it's only joined to 2 things. So you've got 4 colours, 2 of them you're not allowed to do, you can use one of the remaining 2 colours. So actually in this way, right, you can reduce your graph, and so actually, right, we've got rid of part of the graph, you can also get rid of this by exactly the same considerations. So as you can see, by getting rid of small degree nodes, we've actually, we've halved the size of this graph we have to check. So that is just one very basic idea of a reduction. There are a lot more clever ideas in the ways that these graphs are reduced, which I don't really have time to talk about today. But hopefully you appreciate the idea that what mathematicians have done is they've said, okay, actually, let's use some maths, let's show that it suffices to consider only a small set of graphs and check these cases, because in fact, all other graphs can be reduced to these cases. So then we just have to check these cases, and that's what they ask the computer to do. Okay, so a proof exists of this fact. So it's actually called the 4-color theorem, the fact that any map can be colored in 4 colors. But as a mathematician, we're not very happy about the idea of a computer-aided proof. And why is that? Well, because the proof doesn't really tell us anything about why it's true, right? So we've said any graph can be reduced to one of some huge number of graphs, which is far too many for a human to go away and check. The computer's checked it, okay, it's true. Wouldn't it be much nicer to somehow have a reason to understand really the heart of the problem? Why is this true? So a lot of the time, people prove very cool mathematical theorems, then other people come along and they find different proofs which actually draw out the heart or the reason why something is true. So sometimes it's not enough to know something is true. You also really want to understand the reasons behind it. So yes, we're very happy a proof exists. It's not very intuitive. It doesn't tell us why this thing should be true. And we're actually quite far from understanding why. So there's many areas and kind of directions of research have stemmed out of people trying to understand the underlying structure behind these objects in such a way that they can say, look, we actually know mathematically this is the reason why we can always colour it in 4 colours. And we want to say something that isn't just we've checked all the cases. No, we want to say, look, this collection of objects has this very nice property. Oh, that property means we can colour it using 4 colours. And that would make us a lot more happy, I think. So there's actually many interesting directions of research that are still continuing to study these structures, these planar graphs, and the properties of them, and really to understand the heart of why they can always be coloured in 4 colours. Thank you very much for listening.